So in the fifth of our videos on chemical bonding, we're going to look at polarity. And in particular here, we're focusing on the polarity of covalent bonds that we looked at in our last video. Now, polarity arises because of differences in electronegativity across a bond. So we've already talked about what electronegativity is. That is a measure of how much atoms want to gain or lose electrons when they form bonds. And polarity then becomes very, very important when later on we look at secondary bonding, which I also sort of hinted at in the last video. So this concept of polarity builds on what we know about electronegativity and covalent bonds, and it's going to become very important down the track when we look at secondary bonds between molecules, so between covalently or small covalently bonded compounds. So polarity in a bond occurs because of the uneven sharing of electrons in a covalent bond due to differences in the electronegativity of the two atoms. So let's look at those three examples we looked at in the previous video. Firstly, oxygen, water, and NH3 ammonia. And I'll also do one more example in a little bit more detail. So firstly, in oxygen, both oxygen atoms have the same electronegativity. Each element has its own electronegativity, so both oxygens would have the same electronegativity. So that would mean that this bond here would be what we call non-polar, because there is, well, both atoms have same electronegativity. So if there's no difference in electronegativity, there's no polarity, so it's non-polar. So both atoms have identical electronegativity. As I run out of space. Now, when we look at water, oxygen is closer to fluorine on the periodic table than hydrogen, so oxygen has a greater electronegativity. So that would mean that in this case, oxygen is going to hog those electrons. So if we can imagine those electrons, they won't sit exactly in between the hydrogen and the oxygens. Those electrons are going to sit, if you like, closer to the oxygen, because the oxygen wants the electrons more because it's got a greater electronegativity. So oxygen wants electrons more. Now what this means is that the oxygen overall will be left with a slight negative charge because it's got the electrons closer to it, so it's got, if you like, more share of the electrons. And the hydrogen has less share of the electrons, so it ends up with a slight positive charge. And the way we show this is we put this little delta symbol, which means a slight or a partial negative charge next to the oxygen, and we put the little delta here with a plus to show that the hydrogen has a slight positive charge, and obviously both hydrogens have that slight positive charge. So that letter I've just drawn, that is the small Greek letter delta, which is often used for difference. You may or may not have seen the capital delta, which is a triangle, and that's basically the capital of delta, and that's often used to mean in mass difference. So when we want to talk about the difference between two numbers, we use that delta. And in here, it's a way of saying there's a difference in the electronegativity, but I guess we use the little delta because we only have a partial. So this isn't a full negative charge like on an electron, it's just a partial negative charge. Same here, it's not like a full positive charge on a proton, it's only a partial positive charge. So we use that delta from the Greek alphabet to show that. If we look at ammonia, again, it's fairly similar. Ammonia is nitrogen is closer to fluorine than hydrogen on the periodic table. So if you like, those electrons are going to hang out closer to nitrogen. So because the electrons, if you like, nitrogen has a greater share of the electrons. Remember, nitrogen also has this unbonded pair of electrons up here that gives it the 8 electrons. We'll learn later about why I've drawn ammonia in that shape. For now, it doesn't really matter why I've drawn it like that. We will cover that later. And I have talked to you about that, so you might be familiar with it, but don't stress on that. And so that means that the nitrogen would have that slight negative charge, and all these hydrogens would have that slight positive charge. So they, like in the other case, would all be polar bonds because of that uneven distribution of the electrons in the bond. And we'll go through one more example, and I'll go through this with both the electron dot diagram and with the bonding. So we have carbon in the middle. Carbon has an electron configuration of 2,4, so it has 4 electrons. Oxygen comes along with its 6 electrons. And we have 2 oxygens, both with 6 electrons. And we can see here, this oxygen thinks it's got 8, so it's happy. This carbon thinks it's got 8, so it's happy. And this oxygen thinks it's got 8, so it's happy. We have 2 shared pairs of electrons there and 2 shared pairs of electrons there. So when we draw the structural formula, we get a carbon in the middle. Sorry, I'll just try and be a little bit consistent with colours. And we have our 2 oxygens like that. Now, which one is closer to fluorine? Well, oxygen is closer to fluorine than chlorine. So in this case, the electrons are going to hang out closer, if you like, to the oxygen. So they'd have a slight negative charge. And that means the carbon wouldn't quite get its full sharing of the electrons, so that would have a slight positive charge. So here, we would have 2 polar bonds. Now, later on, I don't need to cover this now, but just so you know it's coming, when we decide whether a molecule is polar or not, we look not only whether it's got polar bonds, so this CO2 has polar bonds, ammonia has polar bonds, NH3, water, H2O, has polar bonds, whereas oxygen here doesn't have polar bonds, it's non-polar. But when we decide whether a molecule is polar, we look at both the bonds, but you also look at the symmetry. So both water and ammonia are not symmetric, whereas carbon dioxide is symmetric. So in a symmetric molecule, the polar bonds cancel out and it becomes non-polar overall. You don't need to know about that now. I'm just flagging that is coming though in the future. For now, you just need to be able to look at these structures, look at the electronegativity of the atoms making up the bonds, work out if there is a difference in electronegativity, and therefore if the bonds would be non-polar or polar, and which end would be the negatively charged end and which end would be the positively charged end. So a lot of big fancy words there and new symbols, but hopefully it brings together what you know about electronegativity, and now you know why learning about electronegativity is so important, and you can get an appreciation of what makes a polar bond or a non-polar bond. And the rest will come later in more detail. Thank you.